Lesson: Training deep neural networks, optimization and backpropagation. Training deep neural networks is a complex yet rewarding endeavor, pivotal to the development of cutting-edge artificial intelligence applications. At the heart of this process lies optimization and backpropagation, two critical methodologies that underpin the learning capabilities of these sophisticated models. Optimization in neural networks refers to the process of fine-tuning the model's parameters to minimize the difference between the predicted and actual outcomes, a process guided by a loss function. Backpropagation, on the other hand, is the algorithmic approach used to compute the gradient of this loss function with respect to each weight by the chain rule, effectively enabling the network to learn from its errors. At the core of training deep networks is the need for efficient optimization algorithms. Gradient descent is the cornerstone of these algorithms, where the key objective is to minimize the loss function by iteratively updating the model weights. In practice, different variants of gradient descent are employed, such as stochastic gradient descent, which updates weights more frequently and can often converge faster than standard gradient descent by using a subset of the data. However, SGD can be noisy, leading to oscillations in the path towards convergence. To address this challenge, advanced optimization algorithms like ATOM have been developed. ATOM combines the benefits of two other extensions of SGD, adaptive gradient algorithm and root mean square propagation. It adapts the learning rates for each parameter, combining the advantages of both ATAGRAD, which works well with sparse gradients, and RMS-prop, which performs well in online and non-stationary settings. These adaptive learning rate strategies have proven effective in accelerating the convergence of deep networks and improving their performance across various tasks, such as image and speech recognition. To implement these optimization strategies effectively, practitioners often rely on powerful frameworks like TensorFlow and PyTorch. TensorFlow, developed by Google Brain, offers a rich set of functionalities that facilitate the construction and training of deep learning models. Its automatic differentiation capabilities are integral to implementing backpropagation, allowing practitioners to focus on model architecture and training without worrying about the mathematical complexities of gradient computation. PyTorch, an open-source machine learning library developed by Facebook's AI Research Lab, provides an intuitive interface and dynamic computation graph, making it a popular choice for research and development. Its seamless integration with Python and support for GPU acceleration enables rapid prototyping and deployment of complex models. The practical application of these tools can be illustrated through a real-world example in image classification. Suppose we are tasked with developing a neural network to classify images of handwritten digits, a common introductory problem known as the MNIST dataset. Using a framework like TensorFlow, one can quickly set up a neural network model by defining the architecture, such as a series of convolutional and fully connected layers, and specifying a loss function like categorical cross-entropy. The next step involves selecting an optimizer, such as ATOM, and setting hyperparameters like learning rate and mini batch size. With the model and training parameters in place, TensorFlow's automatic differentiation and execution engine streamline the backpropagation process, updating the model weights iteratively as it learns from the provided images. Despite the robustness of these tools, training deep neural networks is fraught with challenges, including overfitting, vanishing, and exploding gradients, and the need for extensive computational resources. Overfitting occurs when a model learns the training data too well, capturing noise instead of the underlying pattern, which leads to poor generalization to new data. Techniques such as dropout, where randomly selected neurons are ignored during training, and L2 regularization, which penalizes large weights, are commonly employed to mitigate this issue. The vanishing and exploding gradient problems are particularly problematic in very deep networks, where gradients can become exceedingly small or large, preventing effective learning. The use of activation functions like ReLU has been instrumental in overcoming these issues by maintaining a constant gradient across much of the input space, thus facilitating the training of deeper models. Additionally, techniques like batch normalization, which normalizes inputs for each mini batch, have been shown to stabilize and accelerate training by reducing internal covariate shift. Computational resources also play a crucial role in the training of deep networks. The demand for high-performance hardware, particularly GPUs, cannot be overstated. The parallel processing capabilities of GPUs significantly reduce training time, enabling the handling of large datasets and complex model architectures that would be impractical on traditional CPUs. Cloud-based platforms like Google Cloud AI and Amazon AWS offer scalable solutions for deploying and training models, providing access to powerful computing resources without the need for substantial upfront investment in hardware. To further illustrate the effectiveness of these methodologies and tools, consider a case study in natural language processing. The development of language models, such as BERT, showcases the application of deep learning in understanding and generating human language. BERT's architecture relies on a transformer model that leverages attention mechanisms to capture contextual information in text, trained using a two-step process involving masked language modeling and next sentence prediction. The use of optimization techniques like Atom and frameworks like TensorFlow have been pivotal in fine-tuning BERT for various NLP tasks, including sentiment analysis, question answering, and named entity recognition. In conclusion, the training of deep neural networks is a multifaceted process that hinges on the effective implementation of optimization and backpropagation techniques. The advancements in optimization algorithms, coupled with powerful frameworks and computational resources, have significantly enhanced our ability to develop and deploy sophisticated AI models. By understanding and applying these methodologies, professionals can address real-world challenges, from image classification to language processing, and harness the full potential of deep learning in their respective fields.